In last lecture, we have seen nature of the orbit in a central force field, and we have also derived the different equations for the different shapes of the orbit. We have also derived the equations for the different shapes of the orbit. Now we are going to deal with the stability of the orbits. So there is a condition for the stability of the orbits which states that so d square v effective upon dr square. So that must be greater than 0 for r is equal to r naught. We have already seen the graph of that v effective versus r. So when the value of this so this is the graph of the v effective versus r. So this is v effective and this is r. So for the value of this r is equal to r naught, uh, so this is some sort of a boundary condition. So d square v effective upon dr square, that must be greater than 0. Then and then only the orbits will attain the stability. Now let us consider a potential of the form v of r is equal to minus k r raised to n plus 1. So we have taken the particular potential because it represents the bounded motion equation. So this is the mathematical form of some bounded motion, and we have taken a potential of this form. Okay, now if we put the value of this v of r in the equation of the v effective, then we are going to get v effective is equal to minus k r of n plus 1 2 m r square. So let me call it as the equation number 1. Now if I take the derivative of this equation 1, because I need to go for this condition, so let me take the derivative of v effective upon dr is nothing but n plus 1. So minus will be there, k r is to n minus, so this will be L square upon m r cube. So the derivative of this, when this r goes upward, so it will become minus and that 2 will get cancelled. Okay, so this is just a mathematical form. You just check it out for yourself. Okay, let me call this as a equation number 2. Okay, now if I calculate, so or let me put the value of this delta v effective upon delta r is equal to 0. So what I'm going to get is minus n plus 1 k r is to n is equal to minus L square upon m r cube. This will not become minus. If I'm taking it on right hand side, it will become plus. So it will be, if I take the value of k into n plus 1, so it will become L square upon m r cube into r raised to n, or L square upon m r raised to 3 minus n, r raised to minus 3 minus n. When this minus uh, when this plus 3 will go into the denominator, it will become minus 3. Similarly, r raised to n, when it goes into the numerator, it will also become r raised to minus n. Okay. Why we have calculated this? Because we want to put this value of this k into n plus 1 into the second derivative. Okay, now let us take differentiation this d square v effective upon dr square. So this is the value of the v effective upon v effective upon dr. So that will be minus n plus 1 k n into r raised to n minus 1 plus L square upon m r raised to 4. 3 will be in the numerator, 3L square upon m r raised to 4. Now let us put the value of this n plus 1 into k, this as a value of this k into n plus 1. So it will be minus L square upon m r raised to minus 3 minus n. Now n is over here and r raised to n minus 1 plus 3L square upon m r raised to 4. Now, so this r minus 3 minus n and this minus n, this plus n will get cancelled, and here we are going to get r raised to minus 4 L square upon m r raised to minus 4 into n plus 3L square upon m r raised to 4. So let us take this r raised to 4 to the denominator. So we are going to get L square upon m r raised to 4 n plus 3L square upon m r raised to 4. So let me take L square upon m r raised to 4 common, and what I am going to get is, so it will be n plus 3. If I take out the minus term common from this, so this minus and minus become plus, and what I am going to left with is n plus 3. Okay, now if we want the value of this left hand side greater than 0, then value of this n must be greater than minus 3. Suppose if we want the value of d square v upon dr square not equal to 0, then for that this n must be greater than 3. So what is the meaning of this? So n greater than 3, it means that, so the value of this n over here, it must be greater than minus 3. So if I take the minimum value as a minus 3, so it will become r raised to minus 2, minus 3 plus 1, it will become r raised to minus 2, and if it is coming to the denominator, it will become r square. And we know that in a gravitational force field, the potential field is of a type of a 1 upon r square. Okay, so 1 upon r square, 1 upon r cube, whatever it is. So if the potential field is of 1 upon r square, then and then only, or if the value of this n is greater than minus 3, so it can be greater than minus 3, it means it can be minus 2, minus 1 or 0 and so on. So if the value of this n is greater than minus 3, then and then only the particle or the planet will revolve in a stable orbit.